This galaxy shouldn't exist. It is too old, too massive, too organized, and too far away to be any of those things. And yet there it sits in the data from the James Webb Space Telescope, staring back at us from a moment in time when the universe was still a screaming infant, when the first stars had barely finished forming, when nothing this big should have been possible. By every rule we thought we understood about how galaxies grow, this thing should have eaten itself by now. It should have torn itself apart in a runaway cycle of star formation, choked on its own gas, collapsed under its own weight, or simply exhausted itself into a faint smear of dying light. Instead, it is calm, it is structured, it is mature. It is by all appearances a fully grown adult galaxy that somehow showed up at a kindergarten birthday party, and nobody can explain it. The James Webb Space Telescope was supposed to confirm what we already believed. That was the quiet expectation among most astronomers when the mirrors finally unfolded in early 2022. The story we had spent decades writing, that galaxies grew slowly, that they assembled piece by piece through countless small mergers over billions of years, that the early universe was a sparse, primitive place dominated by half-formed structures and stellar nurseries that were still figuring out how to make stars at all, was supposed to hold up under the new scrutiny. Webb was the next chapter, not a rewrite. We were going to look further back than ever before, see the first faint embers of galaxy formation, and pat ourselves on the back for having understood the universe so well. That was the plan. The plan did not survive contact with reality. Within months of becoming operational, Webb began returning images that made the people analysing them stop, stare, and check their software for bugs. Galaxies were appearing in places they shouldn't be, at distances that meant we were seeing them as they existed only a few 100 million years after the Big Bang. And these galaxies weren't faint blobs or messy clumps of newborn stars. Some of them looked too organized, too massive, too quiet. The kind of structure that should have taken billions of years to develop was somehow already there in less time than it takes for a redwood tree to grow on Earth. The data didn't fit. The data was the problem. Then came the galaxy that broke everything. It is officially designated ZF-UDS-7329, which is a string of letters and numbers that does nothing to communicate how strange this object actually is. So let's just call it what it functionally is: a ghost. A galaxy that, by every model we have, should not exist in the form it does at the time we are seeing it. It sits roughly 11.5 billion light-years away, which means the light reaching Webb's detectors today left that galaxy when the universe was only about 1.5 to 2 billion years old. That is the equivalent of a teenager in cosmic terms. The universe at that age was supposed to still be in the awkward growth phase, full of small, irregular galaxies banging into each other, slowly stitching themselves into something larger over the next 10 billion years. ZF-UDS-7329 didn't get the memo. When astronomers analysed the spectrum of light coming from this galaxy, they found something deeply unsettling. The galaxy was not just present, it was already finished. Its stars had already formed, billions of them, packed into a structure with about 4 times the mass of our own Milky Way. And then somehow it had stopped. Star formation in this galaxy had effectively shut down. The gas that should have been feeding new generations of stars was either gone or no longer being used. The whole thing was already drifting toward retirement, like a factory that had ramped up production, churned out everything it was ever going to make, and then locked the doors. All before the universe had aged through its own infancy. This is the part where the standard models start sweating. To understand why this is such a problem, you have to understand the conventional story of how a galaxy is supposed to grow. According to the dominant framework, called lambda cold dark matter, Galaxies form inside vast invisible halos of dark matter. These halos act like gravitational wells, pulling in gas, holding it together, allowing it to cool and condense into stars. The halos themselves grow by merging with other halos. Small ones combine into bigger ones. Bigger ones combine into bigger ones still. And over the course of billions of years, you end up with the kind of massive galaxies we see in the local universe today. It is a slow, patient process. The recipe takes time. ZF-U DS-7329 broke the recipe. For this galaxy to exist in the form Webb observed, it would have had to assemble 4 times the mass of the Milky Way in a window of time that, by the standard models, simply isn't long enough for that much matter to gather, cool, condense, and convert itself into stars. And then, on top of that absurdity, it would have had to shut off star formation entirely while still being so young. Massive galaxies in the early universe were supposed to be wild, chaotic, gas-rich engines, still pumping out new stars at furious rates. This one wasn't. This one had already gone quiet. So how did it happen? The honest answer is that nobody is sure. There are a few competing explanations, and none of them sit comfortably. The first possibility is that something is wrong with our measurement of the galaxy's distance. If it is closer than we think, then we are seeing it at a later point in cosmic history, which would give it more time to grow. But the data has been checked and rechecked. The galaxy's spectrum, the fingerprint of its light stretched out by the expansion of the universe, is consistent with a redshift that places it firmly in the very early cosmos. The distance is not the mistake. The second possibility is that we have somehow miscalculated its mass. Maybe the galaxy is smaller than it looks, and we are being fooled by some quirk of light or dust or stellar populations we don't fully understand. Astronomers have explored this. Different teams have run independent analyses using different assumptions, and the answer keeps coming back the same. This galaxy is enormous. The mass is not the mistake. The third possibility, the one that makes everyone uncomfortable, is that our understanding of how galaxies form is incomplete. Maybe the early universe was capable of building structures faster than we ever thought possible. Maybe dark matter behaves differently in dense early environments. Maybe the very first stars, the so-called population 3 stars that no telescope has ever directly observed, were so massive and so violent that they jump-started galaxy assembly in ways our simulations don't capture. Maybe gas clouds in the young cosmos collapsed more efficiently than we believed, skipping steps in the slow merger process. Or maybe something we haven't even considered yet was happening in those first billion years, some physics or chemistry or astrophysical mechanism that we simply don't know about. That last option is the one that excites and terrifies cosmologists in equal measure. Imagine being an architect who has spent your entire career studying how skyscrapers are built. You know the materials, the engineering, the timelines. You can predict, with reasonable accuracy, how long it takes to build a 100-story tower. Then someone hands you a photograph of a fully completed skyscraper that, according to the date on the photo, was built in a single weekend. The building is real. The photo is verified. The date is correct. Now you have a problem. Either the photograph is somehow wrong, which has been ruled out, or skyscrapers can be built in ways you never imagined. There is no third option. Either your understanding of construction is incomplete, or you are looking at a miracle. And science doesn't accept miracles. That is roughly where cosmology stands right now with ZF-U DS-7329 and the handful of other early universe galaxies that have shown up in Webb's data with similar problems. The most striking thing about this galaxy is not just its mass or its age or its distance, it is its quietness. Star formation in galaxies is usually noisy. New stars produce ultraviolet light, ionize surrounding gas, blow stellar winds, eventually explode as supernovae, and seed the next generation of stars with heavy elements. A galaxy actively making stars is full of these signatures. ZF-UDS-732-9 has very few of them. The light coming from it is dominated by older stars, the kind that have already settled into long, stable lifetimes. There is no significant evidence of recent star formation. The factory has been shut down. This is what astronomers call a quenched galaxy. Quenching in this context means the process by which a galaxy stops forming stars. It is something we observe in the local universe all the time. Massive elliptical galaxies, the kind that look like glowing yellow blobs in deep space images, are mostly quenched. They had their star-forming days billions of years ago, and now they are full of old red stars slowly burning through what's left of their fuel. We have decent theories about why galaxies in the local universe quench. Sometimes the central supermassive black hole becomes active and blasts out enough energy to heat or expel the gas the galaxy needs to make new stars. Sometimes interactions with other galaxies strip away the gas. Sometimes the gas just runs out or gets too hot to collapse anymore. But all of those processes take time. They take billions of years to fully shut down a galaxy the size of ZF-UDS-7329. And this galaxy is already done. In less than 2 billion years from the start of the universe, it managed to form 4 times the mass of the Milky Way, complete a full life cycle of stellar generations, and then somehow shut off the entire star-making apparatus. It is not just early, it is impossibly early. If a galaxy this big had truly run away with its own star formation, the way classical models predict for early massive systems, it should have torn itself apart. The kind of runaway feedback you would expect, with supernovae detonating in rapid succession, with shockwaves rippling through the dense interstellar gas, with the central black hole gorging itself and spewing radiation, should have either disrupted the galaxy entirely or kept it in a frantic, chaotic state for billions of years. Instead, this galaxy looks composed, settled, as if it lived through whatever apocalypse forged it and came out the other side calm. It is the cosmic equivalent of finding the wreckage of a ship that survived a hurricane, and the deck chairs are still arranged in neat rows. There is another layer to this puzzle. ZF-UDS-7329 is not alone. It is one of a growing family of early universe galaxies that Webb has uncovered, each of which presents some version of the same problem. Some are even more distant, with light reaching us from when the universe was only a few 100 million years old. These are objects designated with names like CEER S-93316, GN-Z11, JADES-GS-Z14-0, GHZ2. Each one is a small piece of evidence that the early cosmos was busier, more developed, and more structured than anyone expected. Galaxies are showing up too early, too massive, too organized, with too much complexity in their stellar populations and chemistry. The pattern is the problem. If ZF-UDS-732-9 were the only oddity, you could chalk it up to statistical noise. The universe is big. Strange outliers happen, but Webb keeps finding them. Every new deep field, every new survey of the early universe brings back another anomaly. The signal is getting harder to dismiss. Whatever was going on in the first 1 to 2 billion years after the Big Bang, it was something different from what our models have been telling us for 40 years. So what could it actually be? One leading candidate explanation involves the structure of dark matter itself. Dark matter, the invisible substance that makes up about 85% of all the mass in the universe, is the scaffolding on which galaxies are built. The standard model treats it as cold, slow-moving, and forming a smooth distribution of halos that grow by merging. But what if it isn't quite that simple? What if dark matter clumped earlier and more efficiently than we thought? In some alternative models, dark matter halos in the early universe could have been much denser, much more concentrated, much more capable of pulling in gas at extraordinary rates. Under those conditions, a galaxy like ZF-UDS-7329 could have assembled in a far shorter time frame, almost like a cosmic pressure cooker rather than a slow oven. Another idea focuses on the first generation of stars. The very first stars to form in the universe, born from clouds of pure hydrogen and helium with no heavier elements to slow their collapse, would have been monsters. Some models suggest these stars could have been hundreds, even thousands of times the mass of our Sun. They would have lived fast and died spectacularly, exploding as the most powerful supernova the universe has ever produced, and seeding their surroundings with heavy elements at incredible rates. A galaxy that formed in the wake of these first stellar generations might have skipped several stages of the slow build-up process we expect. The seeds were too rich, too fast, too violent. There is also the possibility that early gas clouds collapsed differently. In the modern universe, when a cloud of gas tries to form stars, it has to fight against turbulence, magnetic fields, radiation pressure, and various forms of feedback. These all slow the process down, but in the very early universe, the conditions were different. Gas was denser. Magnetic fields hadn't fully developed. Radiation environments were more uniform. Some simulations suggest that under those conditions, gas clouds could have collapsed almost in free fall, converting much of their mass into stars in just a few tens of millions of years. If that's true, the universe could have built massive galaxies in a flash and then run them dry equally quickly. Another, more radical possibility is that the rules themselves are different. Some cosmologists have proposed that we may need to revise our understanding of the cosmological framework. Perhaps the expansion history of the early universe was different from what we believe, allowing more time for galaxies to assemble. Perhaps gravity itself behaves differently on certain scales. Perhaps inflation, the explosive growth phase that occurred in the first fraction of a second after the Big Bang, left behind structures that seeded galaxy formation in ways our simulations have never captured. Each of these ideas, taken in isolation, is speculative, but the accumulating evidence from Webb is making them harder to dismiss. What makes ZF-UDS-7329 such a powerful piece of evidence is not just that it exists, it is that it is dead, or at least dormant. A galaxy this old, this massive and this quiet, at this early time forces us to confront something uncomfortable. Whatever process built this galaxy, it was extraordinarily efficient, and whatever process shut it down, it was extraordinarily fast. Both ends of its life cycle happened in conditions our models say should not have been capable of producing them. And then there is the most unsettling thought of all. We are looking at one galaxy. One. And we found it because Webb happened to point in its direction during a deep field observation. How many more are out there? How many massive, ancient, quenched galaxies are sitting in the early universe that we simply haven't seen yet? Each one we find tells us that what we thought was a rare anomaly might actually be a common feature of cosmic history. The universe was assembling itself faster, more violently, and more completely than anyone wanted to believe. If you were to travel back in time to the era when ZF-UDS-7329 was finishing its formation, you would not find a primitive cosmos full of awkward proto-galaxies. You would find an environment that was already producing fully formed stellar systems, already running through their life cycles, already populating the universe with the heavy elements that would one day become planets and oceans and people. The pace of cosmic history in those early epochs was breakneck. You would see vast clouds of gas funneling into halos at extraordinary rates. You would see star formation rates so intense that some galaxies were producing thousands of new stars per year, compared to the modest 1 or 2 new stars per year that the Milky Way produces today. You would see supernovae detonating in such rapid succession that the night sky, if you could see it, would be a constant flicker of blue-white explosions. You would see central black holes growing at speeds that defy current accretion theory, ballooning into supermassive monsters in just a few 100 million years. And then, in some of those galaxies, you would see it all stop. The question of why it stopped, and why it stopped so completely in galaxies like ZF-UDS-7329, may be even more important than the question of how it started. Because quenching, real quenching, requires either the removal of fuel or the prevention of its collapse. A massive galaxy in the early universe shouldn't have been able to do either of those things efficiently. There wasn't enough time for the kind of slow gas exhaustion we see in older systems. There wasn't enough mass and structure for the kind of environmental quenching we see in galaxy clusters. And while supermassive black holes can quench their host galaxies through powerful feedback, the timing has to be just right, and the energy has to be enormous. Whatever shut down ZF-UDS-7329 was a hammer blow. This brings us to one of the most intriguing possible explanations. There is growing evidence from Webb and other observatories that supermassive black holes existed in the early universe at sizes that should have been impossible to reach in such a short time. Some quasars have been observed at redshifts, placing them less than 1 billion years after the Big Bang, with central black holes weighing in at billions of solar masses. To grow that big that fast, these black holes either had to be born absurdly large, or they had to feed at rates that exceed what current models say is possible without choking on their own radiation. If ZF-UDS-7329 hosted a similarly oversized black hole during its growth phase, that black hole could have been the executioner. Once activated, a supermassive black hole feeding at full tilt produces enormous amounts of radiation, jets of high-energy particles, and powerful winds that can sweep gas out of an entire galaxy. This is called active galactic nucleus feedback, and in modern galaxies it is one of the leading explanations for why some massive systems quench. If early black holes were already this large and this active, they could have quenched their galaxies almost as soon as those galaxies were finished forming. In other words, the same thing that built the galaxy may have killed it. This is a haunting kind of symmetry. A galaxy that grew faster than physics seems to allow, fed by a black hole that grew faster than physics seems to allow, until the black hole's appetite became its host's executioner. If that is the story of ZF-UDS-7329, then it is one of the most efficient and brutal life cycles we have ever witnessed in the cosmos. The galaxy lived hard, burned bright, and was snuffed out by the very engine at its heart. There is one more piece to this puzzle that deserves attention. The chemistry of ZF-UDS-7329 is itself surprising. When astronomers measured the spectrum of its starlight, they found evidence that the stars had already been enriched with heavy elements, the products of multiple generations of supernovae. This is significant. Heavy elements like carbon, oxygen, iron, and silicon don't exist in the primordial universe. They are forged inside stars and scattered into space when those stars die. To see substantial heavy element enrichment in a galaxy this early means that not just one, but several generations of stars had already lived and died before the galaxy's final stellar populations formed. Each generation of stars takes time to form, live, and die. Even if those generations were running at high speed in the early universe, the chain of stellar life cycles that enriched ZF-UDS-732-9 with heavy elements suggests that real cosmic time was being burned through. The galaxy's existence implies a hidden history, a sequence of fast, violent stellar generations that we cannot directly observe, but whose fingerprints are baked into the chemistry of every star we are now seeing. This is the part that quietly terrifies cosmologists, because it means that our census of the early universe is incomplete. There are things that happened in the first few 100 million years that we have not yet imaged, not yet detected, not yet placed in our timeline. The universe at that age was already running stellar production lines we haven't witnessed, building galaxies we haven't found, and apparently, in some cases, finishing the job entirely before we ever thought it could begin. ZF-UDS-732-9 is a tombstone, and the tombstone is reading us a story we haven't yet heard. To grasp how strange this really is, it helps to understand just how compressed the timeline is. The universe is roughly 13.8 billion years old. ZF-UDS-732-9 finished its main star formation phase by the time the universe was somewhere between 1 and 2 billion years old. That means everything that needed to happen, the gravitational collapse of dark matter halos, the pooling of gas, the birth of the first stars, the chemical enrichment of the surrounding material, the formation of subsequent stellar generations, the assembly of a galaxy 4 times the mass of the Milky Way, and the complete shutdown of all of that activity had to occur in a window roughly equivalent to 7% of cosmic history. If you compress the entire age of the universe into a single 24-hour day, ZF-UDS-732-9 would have completed its life cycle before breakfast. The Milky Way, by contrast, is still actively forming stars today, more than 13 billion years after the Big Bang. Our galaxy has been quietly producing 1 or 2 new stars per year for as long as we have any records. We are still in the middle of our chapter. ZF-UDS-732-9 finished its book before ours had even been printed. This raises a question that haunts everyone who studies early cosmology. What were the conditions that allowed this to happen? Was there something about the local environment of this particular galaxy that supercharged its formation? Was it sitting in a region of space where dark matter had already concentrated to extreme densities? Was it embedded in a cluster of galactic halos that all collapsed in synchronized fashion, feeding each other gas through cosmic filaments at rates we have never measured? Or was it just one of many galaxies in the early universe doing exactly this, while we, with our limited observational reach, have only just now started to see them? Each of these possibilities opens new doors. None of them are comfortable. The implications go beyond just understanding one galaxy. If quenched massive galaxies were common in the first 1 to 2 billion years of cosmic history, then the entire evolutionary history of the universe needs revision. The story we have been telling, where massive galaxies are the end product of slow, repeated mergers spanning 10 billion years or more, no longer fits. If you can build a galaxy 4 times the mass of the Milky Way in 1/10 of the time the standard models require, then either those models are missing something fundamental, or there are physical processes at work in the early universe that simply don't operate today. This is where the story becomes a real scientific crisis, because the lambda cold dark matter model is not just a theory about galaxy formation. It is the foundation of modern cosmology. It explains the structure of the cosmic microwave background, the distribution of galaxies on the largest scales, the observed expansion history of the universe. It has been tested against thousands of observations and has held up remarkably well. To suggest that it might be wrong, or even just incomplete in ways that affect early galaxy formation, is to suggest that we may need to revisit some of the most successful theoretical work of the past 40 years. Most cosmologists do not want to throw out lambda cold dark matter. The model works too well in too many other contexts, but the discovery of galaxies like ZF-U-DS-7329 has forced a serious conversation about what the model might be missing. Maybe it is the physics of small-scale structure formation. Maybe it is the assumed behavior of dark matter on the smallest scales. Maybe it is the way star formation efficiency was distributed across the early universe. Maybe it is something nobody has thought of yet, and this is where Webb earns its existence. Because for decades, theoretical models of the early universe could be built and refined without ever being tested against direct observation. The early universe was simply too far away, too faint, too obscured by intervening dust and gas to see clearly. We had to infer what was happening from indirect evidence and theoretical reasoning. Webb changed that. For the first time in human history, we have an instrument capable of directly imaging galaxies as they were less than 1 billion years after the Big Bang. The early universe is no longer a theoretical playground. It is an observational target, and what we are observing does not match what we predicted. This is what makes the Webb era so important. It is not just that we are seeing further than ever before, it is that we are seeing things that are forcing us to admit our maps were wrong. Consider what it took to even find ZF-U-DS-7329. Webb is parked at a gravitational balance point about 1.5 million kilometers from Earth, far beyond the orbit of the Moon. Its primary mirror, made of 18 gold-coated hexagonal segments, spans 6.5 meters and collects far more light than any space telescope before it. It operates in infrared wavelengths, which is the only way to see galaxies whose light has been stretched so dramatically by the expansion of the universe. Visible light from the early cosmos is no longer visible by the time it reaches us. It has been redshifted into the infrared, where Webb can finally catch it. To find ZF-U-DS-7329, Webb pointed at a specific patch of sky, the ultra-deep survey field, and stared. Long exposures collected photon after photon, building up an image of objects so faint that no previous telescope could see them. Then spectrographs aboard the telescope analysed the light from individual galaxies, measuring how much it had been stretched by cosmic expansion. From that stretching, called redshift, astronomers can calculate how far away a galaxy is and how long ago its light started its journey to us. From the spectrum itself, they can extract information about the galaxy's stellar populations, its chemistry, its star formation history. It is, in essence, a fingerprint reading of an object that no longer looks the way it does in the image we are seeing. The galaxy in the picture by now has changed, but the snapshot it sent us, encoded in stretched light, tells us exactly what it was during the moment of emission. That is what Webb has been doing, reading fingerprints from the dawn of time. And the fingerprints keep telling us strange stories. For each new galaxy Webb examines in the early universe, the analysis follows a similar pattern. Astronomers measure the redshift to confirm distance and cosmic age. They model the spectrum to estimate stellar mass. They compare the inferred properties to the predictions of cosmological simulations. And in case after case, the predictions fall short. The galaxies are too massive. They form too quickly. They sometimes contain stars that are unexpectedly enriched with heavy elements. Some, like ZF-U-DS-7329, ZF-7329 have already stopped forming new stars when the models say they should still be in their growth phase. The accumulated weight of these mismatches is what is forcing the conversation. One anomaly is a curiosity. A dozen anomalies become a pattern. A pattern becomes a problem. A problem demands an explanation. It is worth pausing to consider what kind of explanation might eventually emerge. Science rarely makes progress through a single dramatic discovery. More often, it advances through the slow accumulation of small adjustments, each one nudging the model in a slightly different direction, until eventually the cumulative weight of those adjustments produces a new framework. We may be in the early stages of that process now. The picture of cosmic history that emerges from this work 10 or 20 years from now will probably not be a wholesale rejection of everything we currently believe. It will be a refined, expanded, more nuanced version of the current model, with new physics added in places we did not previously think we needed it. Or it could be something more dramatic. There is no rule that says the resolution to this puzzle has to be incremental. Sometimes science does take a sudden leap. Quantum mechanics, general relativity, the discovery of dark energy, all of these were paradigm shifts that came with relatively little warning. If the early universe turns out to have been operating under conditions that our current physics cannot accommodate, the next chapter of cosmology may look very different from the current one. ZF-UDS-7329 may be a clue to that next chapter, or it may be a curiosity that finds an explanation within the existing framework. Right now, nobody knows for sure. That uncertainty is part of what makes this moment in astronomy so exciting. While theorists wrestle with the implications, observers are pushing forward. New surveys are being conducted. New deep fields are being imaged. New spectroscopic measurements are being taken to confirm or revise the properties of every candidate early galaxy. The data is piling up faster than the theories can absorb it. Conferences and peer-reviewed journals are filled with papers debating the meaning of these discoveries. Some argue that better modelling will eventually reconcile the observations with the standard framework. Others argue that the framework itself is in trouble. The debate is ongoing, and it will likely take years to resolve. In the meantime, ZF-UDS-7329 remains the symbol of the puzzle. The galaxy that should not exist. The dead colossus from the dawn of time. A reminder that the universe, at its earliest stages, was apparently doing things we did not expect. Let's zoom in on what life would actually look like inside such a galaxy, because the abstract numbers can blur into meaninglessness without grounding. If you were a hypothetical observer floating somewhere inside ZF-UDS-7329 during its prime, before star formation shut down, you would be inside one of the most chaotic environments imaginable. The galaxy would be denser than the Milky Way, more compact, packed with bright young stars whose light would dominate everything. The sky around you would not be the dim, scattered starfield we see from Earth at night. It would be saturated. There would be stars visible everywhere, in every direction, with hardly any patches of true darkness between them. Massive stars, the kind that burn through their fuel in just a few million years, would be exploding regularly. From your vantage point, you would witness supernovae lighting up the surrounding space with such frequency that the ambient brightness of the galaxy would never settle into stillness. The interstellar medium would be turbulent, shocked, full of expanding bubbles of hot gas left behind by stellar deaths. The whole galaxy would feel like a constantly detonating arsenal. And then, sometime during the galaxy's first 1 to 2 billion years of life, it would all calm down. The supernovae would become rare. The bright young stars would burn out and not be replaced. The interstellar medium, once turbulent and luminous, would settle into a quieter equilibrium. The galaxy would be left populated mostly by long-lived stars, slowly aging, gradually cooling, casting reddish-yellow light across what was once a stellar battlefield. That is what Webb is photographing. The aftermath, the scene after the war. A galaxy that lived through its violent phase and emerged into something resembling peace, while the rest of the universe was still gearing up for its own first wave of activity. We tend to imagine the early universe as primitive, simple, sparse. The mental image is of a few faint blobs of stars scattered across a mostly empty void, slowly building toward the rich tapestry of structures we see today. That image is wrong, or at least incomplete. The early universe was capable of producing structures so complex and so massive that we are still struggling to model them. It was a place of extreme conditions, extreme densities, extreme star formation rates, extreme gravitational environments. It was not a slow start. It was a sprinting beginning that in some places ran out of breath before the rest of cosmic history had even begun to unfold. This recalibration of our intuition matters, because the way we picture the early universe affects how we understand everything that came afterward. If the early universe was busier, faster, and more capable than we thought, then the conditions for everything that followed, including the formation of solar systems, planets, and possibly life, were also more favourable than we believed. Heavy elements were being produced earlier. Stable galactic environments were emerging earlier. Worlds capable of supporting complex chemistry could have existed earlier. The window for cosmic biology, in the broadest sense, may have opened far sooner than we have traditionally assumed. This does not mean life arose earlier. We have no direct evidence of life anywhere except Earth, and even that single sample took billions of years to develop into the kind of complex biology we represent. But the conditions for chemistry, for stable solar systems, for rocky planets and liquid water, those conditions could have existed far earlier than once thought. The universe may have been hospitable in its rough and brutal way much sooner than we knew. This is the kind of thought that lingers after the data has been processed and the papers have been published. The numbers and the models tell one story. The implications, when you sit with them, tell another. The universe is older than we thought. The universe is younger than we thought. Both are true in different senses. The cosmic clock has been running for 13.8 billion years, and yet many of the structures we see today existed in mature form when that clock was still on its first long tick. There is a sense in which Webb has not just changed our understanding of the early universe. It has changed our understanding of time itself, or rather, it has changed our understanding of what was possible during the time that has passed. The history of the cosmos turns out to be denser, more eventful, and more astonishing than we knew. The empty stretches we imagined between the Big Bang and the modern universe were not so empty after all. They were filled with activity we are only now beginning to detect. Beyond ZF-UDS-7329, the broader pattern of impossibly mature early galaxies is what makes the puzzle most pressing. Some research teams have suggested that Webb is finding too many massive galaxies in the early universe to be consistent with even the most optimistic standard models. If this finding holds up under further analysis, it could indicate a fundamental disagreement between observation and theory. Other teams have argued that the apparent excess might be due to systematic errors in how galaxy masses are measured at extreme distances. The dust around such galaxies, the assumed shape of their initial mass functions, the specifics of how their light is being interpreted, all could potentially be biasing the analysis. The debate is ongoing. Some of the most striking early Webb claims have already been revised downward as more data has been collected and as analysis methods have been refined. But even after these revisions, a population of unexpectedly mature early galaxies remains. ZF-UDS-7329 is one of the most carefully studied of these, and it has survived multiple rounds of independent analysis. Its mass, its age, its quiescent state, all of these have been confirmed by different teams using different approaches. It is real. It is doing what we said it cannot do. The work now is to figure out how. There is an old saying in science that when an instrument finds something that contradicts theory, you have two options. You can question the instrument, you can question the theory. Webb is the most scrutinized scientific instrument ever built. Its calibration has been verified against known objects. Its measurements have been cross-checked against ground-based observatories. The data it returns has been independently analysed by competing research groups. The instrument is not the problem. That leaves the theory. Or more precisely, that leaves whatever pieces of the theory turn out to be incorrect or incomplete. Most of cosmology is in good shape. The expansion of the universe, the cosmic microwave background, the large-scale distribution of galaxies, all of these continue to fit the standard model with remarkable precision. The trouble is concentrated in a specific place, in the early universe, in the era when massive structures were assembling, and in the question of how they could have done so with the speed and efficiency we are now observing. Whatever the final answer turns out to be, it will likely involve adjustments to how we think about dark matter, star formation, and feedback processes in the first 1 to 2 billion years after the Big Bang. It may also involve recognizing that some of our previous estimates about that era were based on assumptions that simply do not hold up at extreme conditions. The early universe was not a scaled-down version of the modern one. It was a different place, and it operated by rules we are only now starting to glimpse. The story of ZF-UDS-7329, then, is not just the story of one galaxy. It is the story of a moment in scientific history. A moment when an instrument we built, launched, and operated revealed that our picture of the universe was incomplete in ways we had not anticipated. It is the story of how science progresses when reality refuses to cooperate with theory. It is the story of what we do next when the data tells us we were wrong. And perhaps most importantly, it is the story of how humility returns to a field that had grown comfortable with its own certainty. For decades, cosmologists could speak with confidence about the first billion years of cosmic history, even though no instrument had ever directly imaged that era. The models were elegant. The predictions seemed solid. The framework felt complete. Then Webb came online, and the field suddenly remembered that the universe is under no obligation to match our expectations. Galaxies appeared that had no business existing. Mature systems showed up in immature environments. Quiet giants sat in places where chaos was supposed to reign. The lesson is one of the oldest in science. The universe is always stranger than we think, always more capable, always more surprising. If you stop and consider what Webb has done in just its first 3 years of operation, the magnitude becomes clearer. Decades of theoretical work, millions of hours of computer simulations, entire textbooks of cosmological understanding are being challenged by a relatively small number of observed galaxies that don't fit. Each new survey adds more pressure. Each new analysis confirms that the anomaly is real. The astronomy community is, slowly and carefully, beginning to accept that the early universe was not what we thought it was. This is not a crisis. Or rather, it is the kind of crisis that scientists secretly love. Because every crisis in physics has historically led to a leap forward. When the planet Mercury's orbit wouldn't fit Newton's laws, that crisis led to Einstein's general relativity. When the ultraviolet catastrophe broke classical thermodynamics, that crisis led to quantum mechanics. When galaxy rotation curves wouldn't match the visible mass of galaxies, that crisis led to dark matter. We are now in another such moment. The galaxy's Webb is finding ZF-UDS-7329, chief among them, are telling us that something in our model is wrong, or incomplete, or both. And the answer, when we find it, will reshape our understanding of cosmic history. The temptation is to look at all of this and feel a kind of vertigo. The universe is older, vaster, and more efficient at building structures than we knew. There are galaxies that lived and died in cosmic infancy. There are processes we don't yet understand operating in the dark depths of the early cosmos. Every assumption we made about the slow, patient growth of structure is being put to the test, but there is also something exhilarating about it. We built a telescope. We launched it 1 million miles into space. We unfolded its mirrors with thousands of precise mechanisms that had to work perfectly the first time. We pointed it at empty patches of sky, and it told us we were wrong about how the universe began assembling itself. That is one of the most important discoveries an instrument has ever delivered. Not because it gave us answers, but because it gave us better questions. ZF-UDS-7329 is not the end of the story. It is a chapter break in a book we did not realize we were misreading. The ones who work on this puzzle now, the cosmologists, the simulators, the spectroscopists, the theorists, are going to spend the next decade trying to rewrite the early universe. New surveys will find more impossible galaxies. New simulations will explore wilder models. New theories will be proposed, tested, refined, and discarded. By the time Webb's mission is complete, we may have a fundamentally different understanding of how the cosmos came to be the way it is. What does this mean for someone sitting on Earth, looking up at the night sky? It means that the stars overhead and the galaxies beyond them and the deep dark of the space between are not the end product of a tidy, well-understood process. They are the descendants of something far stranger than the standard story. They came from a universe that was capable of things our equations did not predict. They are the survivors of an early cosmos that built and destroyed entire galaxies in a fraction of the time we believed possible. And if we extend the implications further, this raises uncomfortable questions about life itself. If the early universe was capable of producing massive, mature, quenched galaxies in just 1 to 2 billion years, then it is also possible that the conditions for planets and chemistry, and possibly even biology, developed earlier than we thought. Heavy elements, those critical building blocks for rocky worlds and complex molecules, were being forged in stellar furnaces almost as soon as the universe could make them. Earth-like planets, in principle, could have been forming when the universe was still in its toddler stage. Whether life could have emerged that early is unknown. But the door is no longer firmly closed. The cosmos was richer, faster, and more developed than we believed, and the conditions for life may have followed a similar acceleration. This thought, even taken cautiously, is enough to make you sit a little quieter in your chair. Webb continues to look. New observations are being scheduled. The next deep field surveys will probe even further into the early universe, hunting for more galaxies like ZF-UDS-7329, looking for the population of quenched giants that may be hiding in the depths. The Vera C. Rubin Observatory in Chile, with its extraordinary wide-field capabilities, will soon begin operations and provide a complementary view of the cosmic past. Future telescopes, ground-based and space-based, are already being designed with the explicit goal of probing the era when these impossible galaxies formed. The hunt is on. And while the hunt continues, theorists are scrambling to update their models. Dark matter simulations are being run with new parameters. Star formation algorithms are being rewritten to account for the conditions of the early universe. Black hole formation theories are being examined for ways to allow faster, larger seed objects. Every piece of the standard cosmological model is being held up to the light and checked for cracks. Some pieces may survive intact, others may need to be replaced entirely. In the meantime, ZF-UDS-7329 sits in the data. A galaxy that should not be. A finished galaxy in an unfinished universe. A massive corpse in a young cosmos. It is an object that, more than almost any other discovery of the past decade, forces us to confront the limits of what we know. Look at it long enough and you start to notice something strange about your own assumptions. We have always told the story of the universe as though it were a slow, patient unfolding. Like a film in which each scene takes its time, each character is introduced, each setting carefully built. But what if that was never true? What if the universe, in its earliest moments, was running at a speed we cannot quite imagine, creating, growing, finishing entire galaxies before the credits of the cosmic origin story had even finished rolling? What if our slow, patient story is a comfortable fiction we told ourselves because we didn't yet have the tools to see what really happened? We have those tools now, and the picture they are returning is wilder, faster, and more violent than the one we have been carrying around for decades. There is something deeply humbling about this. We are a species that has only existed in any meaningful technological sense for a few centuries. We have only had telescopes for a few hundred years. We have only had space-based observatories for a few decades. We have only had Webb, the instrument capable of seeing the early universe clearly, since 2022. In that minuscule sliver of cosmic time, we have constructed a story about how everything that exists came to be. We have written textbooks. We have published thousands of papers. We have trained generations of scientists in a particular framework of cosmic history. And now, with the very first instrument capable of really looking at the era we were theorizing about, the universe is telling us we have been off by significant margins in important ways. This is not a failure of science. It is science working as it should. The whole point of building instruments like Webb is to test our theories against reality and to update our theories when reality disagrees. The universe is the final authority on how the universe behaves. Our job is to listen carefully and to revise our models when the data demands it. ZF-UDS-7329 is the universe demanding a revision. It will take time to figure out exactly what the revision should be. New observations will refine our understanding of the galaxy's properties. New simulations will explore which physical mechanisms could plausibly have produced it. New theoretical work will propose modifications to existing frameworks, or perhaps entirely new frameworks. The conversation will play out in journals, at conferences, in graduate seminars, and in long late-night arguments between researchers. Eventually, a consensus will emerge. The new picture of the early universe will incorporate the lessons learned from ZF-UDS-7329 and its many siblings, and it will be more accurate, more nuanced, and more complete than the picture we currently have. That is the long arc of scientific progress. Slow, contested, sometimes frustrating, but reliable in its eventual movement toward truth. For now, we live in the in-between. The old picture is wounded. The new picture has not yet emerged. ZF-UDS-7329 sits in the data, waiting for us to catch up. It is a quiet, ancient galaxy from the dawn of time, holding secrets that will eventually rewrite our understanding of how the cosmos came to be. And every time we look at it, we are reminded that the universe is bigger, stranger, and more surprising than we knew. There is one more dimension to this story that deserves real attention, and it concerns the supermassive black hole at the heart of ZF-UDS-7329, the silent engine that almost certainly played a role in killing the very galaxy that grew it. We do not yet have a direct measurement of its mass, but we have strong indirect indicators. Galaxies of this size, in the local universe, almost always host central black holes weighing in at hundreds of millions, sometimes billions of solar masses. There is a tight relationship, observed across thousands of galaxies, between the mass of a galaxy's central black hole and the mass of its inner stellar bulge. The relationship is so consistent that it has its own name in astrophysics, the M-sigma relation, and it suggests that galaxies and their central black holes co-evolve, growing together, regulating each other through feedback. If ZF-UDS-7329 followed that relationship, it would have hosted a black hole on the order of hundreds of millions of solar masses, possibly more. That is a colossal engine, capable of releasing prodigious amounts of energy when fed. And in the early universe, it would have been even more dangerous, because the surrounding gas would have been denser, more available, more ready to feed an active galactic nucleus. When such a black hole reaches a critical accretion rate, the energy it releases can overwhelm the gravitational pull of the host galaxy. Radiation pressure pushes gas outward. Powerful jets carve channels through the interstellar medium. Winds sweep across the galactic disk. The end result is that the gas needed for star formation is either ejected from the galaxy entirely or heated to temperatures where it can no longer collapse into new stars. The galaxy, having birthed this monster at its center, watches as the monster turns around and devours its own future. This is the story we suspect played out in ZF-UDS-7329. It is a quiet, brutal sequence of events compressed into a span of cosmic time so short that, by all rights, it should not have been possible. The galaxy formed. The black hole grew. The black hole flared. The galaxy died. The chilling part is how systematic this process appears to be. If ZF-UDS-7329 is even remotely typical of a population of early massive galaxies, then this same cycle of birth, growth, and self-immolation may have played out across many regions of the early cosmos. Galaxies that we cannot yet directly observe may have lived and died on similar accelerated timelines. The cosmos in its first 1 to 2 billion years may have been a graveyard of fast lives, a place where stellar systems blazed up, peaked, and went silent before the sky had even finished filling out. That is a striking image to sit with. The universe as a place where extraordinary structures rose and fell in cosmic eye blinks, while the rest of the cosmos was still figuring out how to assemble itself into the slower, more patient galaxies we live in today. And we, on Earth, are descendants of that slower, calmer cosmos. The Milky Way is one of the patient ones. It assembled gradually, through countless small mergers, building itself up over more than 10 billion years. It produced stars at modest rates. It hosted a black hole that, while supermassive, never went on the kind of rampage that would have shut down the whole galaxy. As a result, the Milky Way is still here, still making stars, still capable of producing solar systems and rocky planets, and evidently life. If we had been born in a galaxy like ZF-UDS-7329, we would not be here at all. There would have been no time. The whole life cycle of star formation in such a galaxy was over before the kind of stable conditions needed for biological evolution could have lasted long enough to matter. The fast galaxies of the early universe were sprinters. They did not have the patience for chemistry to find biology. They burned themselves out. The Milky Way is a marathoner. So is most of what we see in the local universe. We are the descendants of the slow ones, the patient ones, the ones that did not eat themselves before they could make us. That contrast between the fast lives of early massive galaxies and the long, slow life of our own galactic home is one of the more humbling lessons emerging from this Webb era. Not every galaxy got to last. Not every galaxy got to be a home. Some lived hard and died early, and they left only their light behind, travelling for billions of years to reach our telescopes and tell us what they were. ZF-U DS-7329 is one of those messages. A photon-by-photon transmission from a galaxy that completed its existence before our own home had even started to take shape. A signal sent from a place that no longer behaves the way it did when it sent the signal. A cosmic letter mailed across 11.5 billion years, finally arriving in our era, decoded by our instruments, telling us a story we are still trying to understand. And we will keep looking. We will keep building bigger and better telescopes. We will keep refining our theories. We will keep trying to make sense of the universe that keeps refusing to behave the way we expect. ZF-U DS-7329 is one chapter in this ongoing process. The next chapter is already being written, and the one after that, and the one after that. The story of the universe is far from finished. Our role for now is simply to keep listening, keep observing, keep humbling ourselves before the strangeness of what is out there. The universe was old before it had any right to be old. The galaxies were finished before they should have started. The story we thought we were telling about cosmic history was incomplete and probably wrong in places we have not yet identified. That is what Webb has shown us. That is what ZF-U DS-7329 means. And it is just one galaxy, one in a growing collection of impossibilities. The next decade is going to reshape our understanding of the universe in ways that right now we can only guess at. The map is being redrawn. The history is being rewritten. The early cosmos is no longer the dim, slow, primitive nursery we believed in. It was a furnace. It was a workshop. It was a place where galaxies were born, lived and died at speeds we are only now starting to comprehend. And every time Webb opens its eye to a new patch of sky, it brings back another piece of the story, another impossible object, another reminder that we live in a universe that has been outpacing our models since the beginning, and that the most extraordinary thing about cosmic history is not how slowly it unfolded, but how breathtakingly fast it actually moved. We are still catching up. We may never fully catch up, but we are looking harder and deeper than ever before, and the universe is answering. Sometimes the answers are beautiful, sometimes they are terrifying, and sometimes, like with ZF-U DS-7329, they are simply impossible, sitting in our data, waiting for us to figure out how to make sense of them. There is one final consideration that deserves to be raised before this story closes. We talk about ZF-U DS-7329 as a single object, isolated and strange. But in a sense, it is a member of a hidden community. A community of early universe galaxies that grew fast, lived hard, and went silent before the cosmos had finished its first long inhalation. We have only identified a handful of these so far. The rest are out there, scattered across the deep sky, waiting for our instruments to detect them. When we eventually catalogue more of them, when we have not just one Webb-detected example but dozens or hundreds, we will be able to start asking different questions. How common were quenched massive galaxies in the early universe? Where were they distributed? Did they cluster in particular regions? What was the population of central black holes inside them? What chemistry did they carry? What kind of stellar populations did they leave behind? How do their descendants connect to the galaxy populations we see in the modern universe? Each of these questions is a research program. Each of them will take years or decades to answer fully. But the answers, when they come, will give us something we currently lack. A real understanding of the early universe as it actually was, not as we previously imagined it. The texture, the diversity, the rhythms of cosmic structure formation in the first 1 to 2 billion years will become clearer. The role of objects like ZF-U, DS-7329 will be placed in proper context. The picture will sharpen, and that picture will inform everything else. It will affect how we model the formation of galaxy clusters. It will affect how we understand the origin of supermassive black holes. It will affect how we estimate the timing and prevalence of heavy element production. It will affect how we calculate the evolution of the cosmic web of large-scale structure. The first 1 to 2 billion years of cosmic history is the foundation on which everything else has been built. Getting that period right is essential for getting everything else right. That is why ZF-U DS-7329 matters so much. Not just because it is a strange galaxy, but because it is part of a crucial gap in our knowledge that is finally beginning to be filled. There is a poetic kind of justice in this. We built Webb to see further. We see further. The universe, for its part, sees us back. It shows us things we did not expect, things we cannot yet explain, things that will keep us busy for decades. The relationship is a conversation. The instrument speaks, the universe answers, and the answers are reshaping our self-understanding as a species that thought it had figured out the rough outline of cosmic history. The truth is, we are still in the early stages of figuring it out. We may always be in the early stages. The universe is so vast, so old, so complex, that no telescope, no theory, no human civilization will ever fully capture all of it. But we keep looking. We keep building better instruments, we keep refining our models, and we keep being surprised in ways that humble us and excite us in equal measure. ZF-U DS-7329 will be remembered as one of the discoveries that defined this era of astronomy. Not because it was the most beautiful, or the most distant, or the most extreme by every measure, but because it forced a question that the field had not been asking. How does the universe build a mature galaxy faster than physics seems to allow? How does it shut off star formation in a structure that should still be growing? How do all of these things happen in a window of time so short that our best simulations cannot reproduce them? The answers, when they come, will not just be about ZF-U DS-7329. They will be about the universe itself, about the rules that governed its earliest epochs, about the conditions that gave rise to everything that followed, about the deep history of the cosmos that we are still, billions of years later, only beginning to read. There is a certain weight to looking at an object like this, to know that the photons hitting Webb's mirror left their source when our solar system did not exist, when Earth had not formed, when the elements that would one day become you and me were still scattered as gas in a galaxy other than this one. The light that ZF-U DS-7329 sent us is older than every rock on Earth. It is older than the sun. It is older than nearly everything we can touch or see in our local environment. By the time that light arrived at Webb, it had been travelling for almost the entire age of the universe. When you stare at the image, you are looking at something that may no longer exist in any recognizable form. The galaxy itself, in its present moment, has evolved further. It may have collided with other galaxies. It may have been torn apart or merged into a larger structure or settled into a quiet retirement among the elliptical giants. We will never know. The light that reaches us is a fossil, perfectly preserved in transit, carrying information about a moment that has long since passed. This is one of the strangest aspects of astronomy. Every observation is a kind of time travel. Every galaxy we see is a galaxy as it was, not as it is. The deeper we look, the further into the past we travel. ZF-UDS-7329, as we see it, is a galaxy from when the universe was a child. The galaxy itself has lived through the entire intervening time, evolving and changing in ways we cannot directly observe. We have only the snapshot, the ghost, the frozen moment. And that frozen moment is enough to upend our theories. The story of cosmology in the next 20 years will be the story of how we accommodate this and other discoveries from Webb and its successors. It will involve revisions to our understanding of dark matter. It will involve new models of star formation. It will involve revised theories of black hole growth. It will involve perhaps an entirely new framework for thinking about how cosmic structure assembles in the first place. The work has already started. The papers are being written. The simulations are being run. The conferences are being held. The community is mobilizing slowly and carefully to absorb what Webb has shown us and to reshape our understanding accordingly. In the meantime, the galaxy waits. 11.5 billion light-years away, in a patch of sky most people will never look at directly, sits a relic from the dawn of time. A massive, ancient, quiet structure that should not exist in the form it does. A challenge to everything we thought we knew. A reminder that the universe is not a static thing we have figured out, but a living, evolving entity that is always one observation away from surprising us. For now, we can only sit with the mystery. A galaxy that finished its story before its story was supposed to begin. A massive, quiet, ancient ghost staring back at us from the dawn of time. A reminder that our place in this universe is not as small observers of a well-understood machine, but as curious explorers stumbling through a cosmos that is, in every direction we look, deeper and stranger than we ever imagined. Until then, the ghost galaxy waits, patient, quiet, already finished. A relic from a cosmos that built itself in a hurry, then went silent, leaving us to wonder what happened in those first frantic billion years that we have only just begun to see. Thanks for watching, and I'll see you in the next one.